Hey guys, today we will discuss about an important theorem of uniform continuity. The theorem is if f is continuous on AB, then f is uniformly continuous on AB. So let's discuss. This is our theorem. Here AB is an closed interval and here f is continuous. This is given. And now we have to prove that f is uniformly continuous on this closed interval. So let's start. So here given that f is continuous on AB. So first let's write this. Now we have to prove that f is uniformly continuous on AB. So we can assume that f is not uniformly continuous on AB. Then if there is any contradiction, then we can easily prove that if f is obviously uniformly continuous on AB. So first assume this. If possible, let f is not uniformly continuous on AB. Now here f is not uniformly continuous by our assumption. So from the definition of uniform continuity, what we can say? So from the definition of uniform continuity, there is an epsilon greater than 0 such that for every delta greater than 0, there exists points x, y in AB such that mod of x minus y less than delta, but mod f of x minus f of y greater or equal to epsilon. Because here f is not uniformly continuous, so obviously this will be greater or equal to epsilon. Now we have to take the value of delta. Here delta greater than 0, so we can take delta is equal to 1, half, etc. So let's take. Now when delta equal to 1, then by this definition we get that there exist points x1 and x2. We assume 2 points in AB such that, so by this definition we can say x1 minus y1 less than 1, but f of x1 minus f of y1 greater or equal to epsilon. Again, if we take delta equal to half, the points are x2, y2 in AB such that x2 minus y2 less than half. But similarly, f of x2 minus f of y2 greater or equal to epsilon. So proceeding in this way, we get a bounded sequence. So let's write this. Named as xn and yn in AB such that, so here proceeding in this way, we similarly get that mod of xn minus yn less than 1 by n. Okay, so let's write this. But xn minus f of yn greater or equal to epsilon. Okay, here n belongs to capital N. For all integral values of n, we get this. Okay, now these are two bounded sequence. So here we get subsequence of these sequences xn and yan have subsequences xnk and ynk, and we assume that these two subsequences converges to respectively x0 and y0 in AB. Okay, thus from this condition, these are subsequences, but actually these are also sequences. So this condition holds also for them. So let's write this. One by nk, but xnk, ynk greater or equal to epsilon. For all nk belongs to capital N. And we have to mention that these subsequences converges to x0 and these subsequences converges to y0. Now we use this condition. xnk, ynk less than 1 by nk. So this implies that limit of x and k minus y and k is equal to 0. Now using the property of limit, we can say limit of x and k is equal to limit of y and k. Now here, this sequence converges to x0 and this one converges to y0. Then here, it will be x0 is equal to y0. Okay. Now, so we get that the converging points are equal. Now, from this condition, greater equal to epsilon belongs to capital N. This implies that these two sequences, f of x and k and f of y and k, do not converge to f of x0 and f of y0. So let's write this. This sequence and this sequence. F of x0 and f of y0. If f is continuous, then these two sequences obviously converge to these 2 points, this one or this one. If not, then obviously f is not continuous at x0. So from this, we can say that f is not continuous at x0 in AB. So this contradicts and this contradicts. Hence, f is uniformly continuous on AB. Okay. Done. This on the first part and this is the second part. Okay. So today I end this lecture here. If this video is helpful for you, then please hit the like button and share this video with your friends. So, goodbye.